In this video, we will go over section 4.3, area and definite integrals. We already actually worked with the area under the curve in 4.2. We did it using Riemann sum. The problem that I asked you to try on 4.2 was this one. I asked you to divide into 5 subintervals, right? 5 rectangles, and you found the areas of these 5 rectangles and added them. Now, but you knew that answer wasn't going to be exact. Because take a look at these orange rectangles sticking out of that curve. So we were definitely overestimating the area under this curve, right? But what if we make these rectangles a little bit skinnier, okay? Like, to make this a little more accurate, right? Instead of just 5 subintervals, what if we do like 10 subintervals or 20 subintervals, or why not infinitely many subintervals so that we have infinitely skinny rectangles and add their areas up together, and that will be the area under the curve, right? So that's the idea. We're taking, where's the note? We're taking that Riemann sum and we're taking the limit, we're going to make n all the way up to like infinity. So we're making infinitely many rectangles and add those areas together. That is going to be the area under the curve. And that is the same thing as this notation that we're going to do. Well, you did work with indefinite integrals in 4.1, I believe. Yep. But today, take a look at these numbers that we have up here. We'll go ahead and circle that. Notice there is a number down here. Now, this is the, let's say, left endpoint. This is the left endpoint. And we got another number up here, right? This is the right endpoint of the closed interval. And they are called, the right endpoint is called upper because this is above, right? This is the upper limit. And then the left endpoint is going to be called lower limit. So when we did indefinite integrals, we didn't have these limits. But today we will, because what we are trying to do is we're trying to find the area in this closed interval. And in order for us to find that, instead of really doing the infinite Riemann sum, we're going to use this definite integral. And the fundamental theorem of calculus talks about what this is. If little f, let little f be any continuous function over a closed interval a to b, and the big F be its antiderivative, then the definite integral of little f from a to b is this. Now highlight this. This is going to be the main idea for this lesson today. This is going to be the difference of big F of b minus big F of a. Let me tell you what you know already. You do know how to find the antiderivative big F, right? So it's not difficult if I ask you to just plug in the lower bound and upper bound, evaluate it and subtract it. So this is going to be an easy lesson for you because you do know how to find the antiderivative already. So we're just going to practice. Why not? Review some fraction skills. Why not? I'm going to be evaluating these definite integrals today using this fundamental theorem of calculus, okay? Evaluating definite integrals is called integration, and numbers a and b, now a and b are over here. These are the numbers, are the limits of integration. Note that this word limit indicates an endpoint of an interval, right? Because this is from a closed interval a to b. Okay, the small number goes to the bottom, big numbers go to the top. And these are not limit like limit, but these are just endpoints and not a value that is being approached. All right. But let me show you. I'm sorry. I'm so stuffy. I got sinus infection, guys, and this is horrible. I'm glad I don't have corona, but sinus infection is horrible. I'm so stuffy. All right, it is often convenient to use on intermediate notation, and you'll see me using this very often. Because first I'm going to find the antiderivative using integration, the power rule that we talked about in 4.1. And then before I go straight in, I'm not going to go straight into substituting. I will first find my antiderivative and then write this in a little different notation, right? Notice how we put this antiderivative in a square bracket. Okay, put that in a square bracket. And we put the upper limit on top and lower limit in the bottom. This is me getting ready to go to the very next step, okay? So I'll find antiderivative first, put that antiderivative in a square bracket, put the limits on top and bottom, and then I will do my subtraction after substitution, okay? So that's just an intermediate notation that I will start using from this section, okay? Well, so let's do this. Find the area under the graph of little f of x equals 121 minus x squared over negative 11 to positive 11. Now, the method that you and I talked about gives us an approximate area. The Riemann Sum Method, I mean, you can approximate the area by sketching a curve. We don't really need to sketch it, but we can decide on the number of subintervals, create equal widths rectangles, find the area of those rectangles, and add them all up together, right? That's going to be an approximate area, but now we're not really trying to find the approximate area. We're going to try to find the exact area. So if we can do this. We can do limit as n approaches infinity of Riemann sum as I goes from 1 to n of f of xi times delta x. That's the method that we did. We just didn't have infinitely many subintervals. We just had like, what, 5 subintervals or 4 subintervals. But we can't really do that. So what we're going to do is we're going to use the fundamental theorem of integral calculus. We will, now by the way, what are my limits here? The lower limit, the end point. A is negative 11 and B is positive 11. So let's go ahead and put the limit on this integral notation. Put the negative 11 down here and put positive 11 up there. And put the function f of x inside. The function is 121 minus x squared. Okay? And then what? dx. So instead of doing the left side, because we're not going to add up infinitely many rectangles, we're going to actually just evaluate this what? This integral, in this definite integral. And how do we do this? We're going to use that rule. We're going to use that rule. Fundamental theorem of calculus over here. So first find the antiderivative. And you do know how to find the antiderivative using the power rule. So let me work with 121. That's going to turn into 121 x, right? To the first power divided by 1. But that's just going to be 121x. Minus x to the what power? The new exponent is 3. You increase the power by 1, and don't forget to divide by the new power of 3 right here. Now this is what I'm about to do that intermediate notation. Put these guys in a bracket for me. Put that antiderivative in like a bracket, and then put 11 on top and negative 11 in the bottom. Okay, this is that intermediate step. What this is saying is I'm about to do dismiss. I'm about to do that. Okay, so first, plug in what number? 11 into your x. Put 11 into your x. Everywhere you see x, you're going to plug in 11. Okay? So you're going to get that notation. This work. 121 times 11 minus 11 cubed divided by 3. Okay? That's the first thing that you're going to have. And what we just did, this is big F of 11. This is big F of 11. Okay? Now, what do? We have to subtract, right? Let me erase this. I don't want to confuse anybody. We're going to subtract this by, now this time you're going to plug in negative 11 everywhere you see x. Okay? I'm going to plug in 121 times negative 11 minus negative 11 over 3 divided by 3. Okay, so now what we are looking at is just nothing more than what? Cubing numbers, multiplying and subtracting. At this point, we can go ahead and just type this into our scientific calculator. Let me do that with you, okay? I'm going to take a picture of these. And you know, while I'm on my... let me go ahead and see... Oh, there it is. All right, type in the purple minus orange part that I set up. 121 times 11 minus a fraction, 11 to the third power over 3. Oopsies. Close the parenthesis. That was big F of 11 minus, now let's plug in the negative 11 to the big F, 121 times negative 11 minus, and in the fraction, right? And the numerator was negative 11 cubed divided by 3. Close the parenthesis. All right, let me hit enter. Ta-da! And that is the area under the curve. But while I am here, I want to just show you, okay, because it's possible to, if you have this, if you have your, all of your calculus, I think it does it. Remember, we were evaluating a definite integral, and the function was 121 minus x squared, right? And then the limits were from negative 11 to positive 11. Oh dear, no, what's that? Oh, they gave me a crazy big number. What are you? Go away. I got this weird looking screen up. Well, oh no. I don't know what I did. Okay, let me try to type in 121, 120. Oh my gosh. All right, let me try again. 121 minus x squared, negative 11. Go up and type in positive 11 for the upper bound, and then x. Now, this is just me kind of, no, I don't want to say cheating, but this is just me kind of checking my answer. Ta-da. So, guys, I'm not going to give you a single, hey, evaluate this definite integral, because that's too easy. I know you can just get the answer by plugging this in, but I want you to still practice your math skills by hand, because, in the fall semester, you'll be back to school. And if you have another math class, and if you haven't been doing any math, because you were typing things into your calculator all summer on all fall, that's not going to be good. So make sure that you practice your fraction skills, okay? So that is the area under the curve, and you saw how I checked it using my definite integral function on a scientific or graphing calculator. But that's really what we are going to do, okay? That's how you can find the area under the curve. So instead of finding the Riemann sum and taking the limit as n approaches positive infinity, we can just set up a definite integral with the bounds using the endpoints and evaluate that, okay? All right, let's practice a couple more. Here's example 2. Find the area under the curve of g of x, who is 9 over x over 1 to 6. Now, we do know how to set this up. So set it up as, what are the bounds? 1 to 6, right? And then the function is 9 over x. Let me rewrite this as 9 times what? X to the negative first power. 9 times x to the negative first power. And then dx. And we have to use our, what skill? Our integration skill, right? Now, think about this one. Remember this? Can I apply the power rule here? Like, can I go ahead and increase the power by 1? Here's the question. Power rule that we love. Can I increase the exponent by 1? By the way, if you go up from negative 1, you're going to go to 0, right? And then you have to divide by what? The new power of 0. Can I apply that here? Not really, right? No. So, got to remember something. And maybe it's easier to remember, how do you find the derivative of natural log of x? Okay, and that was 1 over x, right? So, I think we did that in 4.1. Indefinite integral of 1 over x dx is going to be natural log of absolute value of x plus c, and that's the rule that we talked about. And I put an absolute value sign around x there because I wanted to just match the domain. But look at the interval for me right here. The interval is from positive 1 to positive 6. It's all positive anyway. So what I can do is I can go ahead and evaluate this as 9 times natural log of just x. I don't really need the absolute value symbol here because look, the interval is completely positive, so that's okay. We can just write this x positive. And then remember that intermediate notation. I'm going to go ahead and evaluate this from 1 to 6. And what that means is I'm going to first plug in 6 into this function. 9 times natural log of 6. And then what do? Minus 9 times natural log of what number? 1. Okay, that is 9 times natural log of 6 minus 9 times, now I'm telling you, you know this, what is natural log of 1? In other words, what do you have to raise e to so that you get 1? That must be 0, right? So natural log of 1 is simply 0. Therefore, your final answer is 9 times natural log of 6. So great review of 4.1 where we cannot use the power rule. Remember, power rule doesn't apply when n equals, the exponent equals -1. Then you have to use the natural log property, natural log rule there. So this was a good review, but the new lesson that we're talking about is how we are finding the antiderivative and we're subtracting after plugging in our lower and upper limit, okay? Now, this is the part where we do just indefinite integral party over here. We got 6 problems. All right, let me go over those with you right now, okay? So let's evaluate each of the following, starting with this. Now, I know these are the types of problem where you can simply type it into your calculator, but like I said, practice, practice. And on the exam, I'm not going to put any of these. I'm going to make sure I give you some of the critical thinking problems. And you'll see, like this week, I'm not going to assign any daily problems because you will be busy working on your exam 3 practice problems, and the Google Doc is open there for you. It's available on Canvas for you, and I already picked the daily problem for 4.3. And what you will notice is, this is a document. Do you have any integral symbol anywhere? Not really, right? Now, but I got something here from section 4.3, after going over the examples and I'm teaching you the skills to solve 4.3, I will ask you to try number 7. And after watching the video on example 4, 5, and 6, the application problem, you should be able to do number 7. But I will also go over this with you if anybody emails me about it. Like someone emailed me yesterday, oh, I need number 4. So I did that and I posted that on Canvas. So you let me know. Remember, your exam is Thursday, and I'll have just very similar ones. So you want to make sure that you know how to do all of them before the exam. But notice, you know, the integration skills, that's important that I'll ask you. We'll practice together, but I won't really have any of straight up integration problem on your exam because that's just too easy for us now. Then with the calculator, even if you show me work, I know some of the calculators will show you step-by-step work. So I wanted to give you something more than just these. Well, let's practice because the skill is going to be important when you solve those problems. All right, evaluate each of the following. We're integrating from -1 to 4, and the function is x squared minus x. So first find the antiderivative. So x to the 3rd power divided by 3 minus x to the 2nd power divided by what? 2. Now put this in a intermediate notation. Put this antiderivative in a bracket. Put the 4 on top and put -1 in the bottom. Now this is a great start. Now what are we going to do? We're going to plug in first the 4 in here. So find 4 cubed minus 3 over 3 minus 4 squared over 2. Where did I get that from? I really just plugged in 4 everywhere I saw x, right? Now I need to subtract this by the answer that I will get when I plug in -1 into these two places. Ready? So that will be -1 cubed over 3 minus -1 squared over 2. So if you can set it up that much, well, I don't mind if you're using your scientific calculator to evaluate that. So let me actually do that too. But these are just fractions that we can do by hand, but I want to save some time. All right, on the calculator, I'm going to go ahead and type in parenthesis, fraction 4/3. Not 4/3, what was it? 4 cubed divided by 3 minus 4 squared divided by 2. That was when we plugged in 4 into the antiderivative, right? And then you have to minus what's the other one? Negative 1 cubed divided by 3. I put that 3 on the numerator. 3. And then minus another fraction. This time negative 1 squared divided by 2. All right, if I hit enter, I get the answer is 14.16666, okay? So while I'm here, because I got this great tool that I can check the answer, why don't I go ahead and evaluate this finite or definite integral? By the way, what was the function? Was it x cubed? Was it x cubed? Not x to the third. What was x to the third power? Minus 2x. No. Guys, I forgot the function. X squared minus x. X squared minus x. Gosh. X squared minus x. And then the bounds were from what? Negative 1 to 4. And then dx, right? I want to see the exact same number. Oh no. It's not the exact same number. You know why? Because I typed it in wrong. I typed in negative 1 and negative 4 instead of negative 4. If I hit enter again, yes, that is the right answer. So, always good to check our answers. Why not? If I have this tool available. So the answer is 14.16 repeating. If I want to be very accurate and give them the final answer in fraction, I will just convert that 85 over 6. 85 over 6. This equals 85 over 6. Okay? All right. I don't think I will be able to. I will be able to, but I don't think I need to go over every single one of them with you. So how about I'll do a couple more. Why don't I do B? D will be just easy, and E and F. I'll do these 3. And then I'll just leave. Because C, isn't that very, very similar to example 2, right? I'll just say C is similar to example 2. And D, it's going to be the same. It's just going to, you have to find the antiderivative and plug in 3 and negative 4. But let me just do the highlighted ones. They look a little different. Okay? So B this time. Now, if you find the antiderivative of e to the x power, what's that going to be? That's going to be just e to the x, right? And the bounds are from 0 to 2. So the answer is going to be 2e to the second power minus e to the 0 power. E squared is just e squared. But what is anything to the 0 power? That's just going to be 1. So here is my exact answer. E squared minus 1. Okay? I can find the decimal answer, but exact answer is good. But why not? Let me find it. E squared. E squared minus 1. That comes out to be 6.389. 6.389. Approximately 6.389. Okay? All right. So you kind of get it right now. It's finding antiderivative, plugging the bounds, and subtracting them. That's really what the fundamental theorem of calculus is saying. That's what we're doing using it. All right. E, we'll now do E. The bound looks just a little different. I wanted to do this one. All right, so if I integrate this 3x plus 1 over x, I will get 3x squared over what? 2 plus, what about if you integrate 1 over x? 1 over x. Now you're going to get natural log of absolute value of x. But here's the thing. Look at the bounds. 1 is positive. E squared is also positive. So do I really need to put the absolute value bars? Not really. I can just go ahead and say absolute value, natural log of x. So that's the antiderivative. Write down that you're going to plug in e squared and 1 and subtract them. So let me go ahead and first plug in e squared in here. I'll have 3 times e squared squared. That's going to be e to the 4th power, right? Over 2 plus natural log of what? E squared. Oh, we can simplify that. So that's what I get from plugging in e squared, right? But now I must subtract this by the expression that I get when I plug in 1. 3 times 1 squared over 2 plus natural log of what? 1. Alrighty, let's go ahead and simplify the red one a little bit further. Now, the red expression is 3e to the 4th over 2. Using the log property, I can go ahead and bring this 2 down in front of it, right? I can bring that 2 down. And the natural log of e will just turn into 1. So that's that. And then let me go and take care of the second one. 3 times 1 squared is going to be 3, just 3 for the numerator. So the first fraction is 3/2. And what about natural log of 1? That's just going to be 0, right? So if I simplify this, can I simplify this? Why not? Without a calculator, let's combine some terms that I can combine. Like 2 minus 3/2, I can combine them. But then the first one, I think I'll just leave it as 3e to the 4th over 2. Because that has an e expression, and I don't want to get a decimal. And 2 is 4 over 2. So if I subtract those two, I will get a positive 1/2. And if I get well, that's the answer. And I may be able to just put it as a single fraction. 3e to the 4th plus 1. This may be a nice one to put on your exam. Over 2, maybe for the final, I'm thinking. So there you go. And if I want to get the decimal approximation, why don't we do that actually? Yeah. And while I'm there, why don't I type this into my definite integral calculator to check our answer together, okay? Okay, so I'm over here trying to get the decimal. The exact answer that we got by hand was 3e to the 4th power plus 1 for the numerator over 2. And that answer is 82.397. Now, why not? I'm here. Let me go ahead and find the answer using my tool. 3x plus 1 over x, right? 1 over x, that was the function. And then it was the x over there. But then the bound were from 1 to e squared. Now, I bet this will just give us the decimal answer, which better be exactly the same. So I'm happy that we got the answer, but now I kind of figured out this may be a nice one to put on your final exam, because I can ask you to give me the exact answer. And well, I never know though. I don't know what's out there. Like, I know some of them will actually give you the exact answer too, in addition to the decimal. But I'll let you know about the final exam soon, which is going to be what? Isn't it already next week? It's going so fast, guys. But the answer for E is 82.397. But this is the exact answer, right? This is the exact answer. And what we got down there is just decimal approximation. All right, let me do one more so that you can go and do the homework problems. And really, no daily problem for this week. Just going to ask you to start working on your practice problem for the exam. Now this one, look at the bounds. Bounds are just variables, a and b. But we know how to do this. Find the antiderivative of 1/3 x cubed. And then we're going to plug in a and b and subtract them. Okay? So what's the antiderivative? 1/3 stays there for there. But increase the exponent by 1, which will be 4. And you're going to divide this by the new power of 4, but that's looking bad, right? I don't want that. So what's the same thing as dividing by 4, guys? What's the same thing as dividing by 4? Multiplying by 1/4, right? So I'll do that. And just kind of temporarily putting them in a bracket with a and b written down as my limits. If I simplify the inside part, I will get 1 over what? 12 x to the 4th. And then I will have BA. Now we're ready to plug in A and B. So if I first plug in B into this, let me just go ahead and put this x cubed on top of this fraction, okay? I'll get B to the 4th power over what? 12, right? Minus, plug in A into x this time, A to the what power? 4th power over 12. So notice they got the same denominator, so maybe I can just write this as B to the 4th minus A to the 4th divided by 12. Now that's all we can do because we don't know what A or B is. So this is where I will stop. Chat. Shh. So when I prepare this notes, I think I just put way too many examples. C is very similar to example 2. I'll skip, and D is just, it's the same. It's the same as almost like problem number 3A. So I'll stop here. I'll ask you to now I want you to try the daily problem and the homework, and please email me if you need me, okay? If you need me to go over anything, let me know, because Thursday morning I will send you your exams, and I want you to be able to practice all these problems really that I posted. I think 2 people are working diligently on it because they've been emailing me about it, but I don't know if the rest of you, saw this already, but I went over just one of them so far, but if you ask me to, if you email me about it, I will also go over the other ones